So in this video, we are actually going to discuss that is matrix tree theorem. Okay, we just going to give the statement of this theorem, and we'll take some example and verify this that is matrix tree theorem. So before going to this that is matrix tree theorem, we need some concept which are known as, first one is actually arborescence in a directed graph. So what is this arborescence in a directed graph? So if I consider this is a directed graph, this is vertex set of Z, and E is the H set. Okay, this directed graph, and you consider U as a particular vertex. U is a vertex. Then Z is called an arborescence converging to U. Okay, G is called an arborescence converging to U if there exists a path from B which is not equal to U to U. Okay, that is from every vertex other than U, there must exist a path. Okay, and out degree of that vertex, this is must be equal to 1. Okay, for every V is not equal to U, and in degree of this vertex U equal to 0. Okay, then we say that Z has an Z is called an arborescence converging to U. Okay, arborescence converging to U. Okay, so in this case, say this is not actually the example of this arborescence converging to U. This is an example of arborescence converging towards actually U. T is an arborescence, it is a subgraph arborescence. Okay, so we actually need this subgraph arborescence, so therefore we are going to discuss this subgraph arborescence. So so you can observe, so if I consider Z is an arborescence converging to U. Okay, Z is an arborescence converging to U. So picture is something like that. Z is an arborescence converging to U means, we just take this picture. Z is an arborescence. So this is our U, say U. The graph should be something like that. This is the graph, say. This is the graph, directed graph. We have directions. Okay, converging to U. So this is a directed graph. Converging to U means now this is something like that. Out degree of each vertex. Okay, out degree of each vertex. Out degree of each vertex. This must be equal to 1. So you can observe out degree, that is the direction outside from the particular vertex, this vertex, that is this is say A, B, C, D. So okay, so out degree, that is this, there is only one edge which here in degree 0, there is no inward direction, so out degree is actually 1 here. Here also out degree is 1, but in degree is also 1 in this vertex, but we need only out degrees. Similarly, out degrees here, this is out degrees, so you have to delete this actually. Okay, delete this to get the corresponding arborescence converging to U. So you can observe here also out degree is, this is out degree is 1, here also out degree is 1. Okay, out degree is 1. Okay, something like that. So therefore this is actually the graph Z is an arborescence converging to U. You can observe out degree of the vertex U is equal to 0. So this is an example of arborescence converging to U. Okay, arborescence converging to U. So we're interested as subgraph arborescence. So you can see, so thus from this observation, thus there exists exactly one such path from B to U. There is no other path actually. Okay, there is no other path. We have only this type of path, because the out degree of this vertex, each vertex equal to 1. Okay, so there is no possibility, okay, to get another arborescence converging to that particular vertex U. Okay, so out degree is equal to 1. So okay, so that is actually the concept of arborescence of a graph which converging to a particular vertex U. Okay, so you can observe there is exactly one such path from any V to U. Okay, this is possible. So a subgraph T is called a spanning arborescence converging to U. Okay, if T is an arborescence towards U, and vertex set of T is equal to vertex set of G. So the concept is same. We have to consider a subgraph actually. In our previous case, this is a the arborescence is defined in the main graph, but here we are going to define the arborescence in terms of this subgraph, where this subgraph contains all the vertices of the graph. Okay, main graph. Okay, all these concepts are there. So here you can see in this graph, you can see we have you consider this red blue edges. Okay, this collection of edges forms the actually corresponding arborescence. Okay, spanning arborescence, because you cover all the vertices. These are the vertices. Okay, you observe all the vertices. Okay, we have counted all the vertices. Okay, and you observe out degree of each vertex. This is one out degree, this is out degree 1. Okay, you just consider red blue line. Okay, and this is also one out degree of this vertex 1. Okay, out degree of this vertex 1, out degree of this vertex 1, out degree of this vertex 1, out degree of this vertex 1. You can observe out degree of this vertex 1, and out degree of this vertex equal to 0. If we are not counting these edges, observe it. Okay, therefore this is actually spanning arborescence. Okay, the spanning the red blue edges from a spanning arborescence converging to U. Similarly, we have the concept of spanning arborescence diverging from U. Okay, the same way in the out degree will be replaced by in degree. Similarly, T is a subset and subgraph of this is a spanning arborescence diverging from U if there is an directed path in T from U to any vertex v is not equal to T, v is not equal to U, and in degree of each vertex equal to 1 for every v is not equal to U, and in degree of that vertex equal to 0, the particular vertex equal to 0. So you will try to construct that kind of actually spanning arborescence which diverging from U. Okay, diverging from U. So we need these term actually. Okay, so T negative Z U, number of spanning arborescence in Z converging to U. Okay, so since out degree is related, okay, out degree of that particular for converging to U, out degree of U is equal to 0, therefore this is actually negative. Similarly, this is positive, this is actually number of diverging from U. Okay, how many actually arborescence are there? Okay, how many arborescence are there? Okay, converging arborescence to U and diverging arborescence diverging from U, how many arborescence are there? So the graph Z contains, you can observe no loops, because if I consider loop actually here, if I consider a loop, so if I consider a loop, it will not actually harm actually. You can delete it will not affect the actually concept of arborescence, whether it is diverging, whether it is in converging, it will not affect. Okay, so you can remove this loop. So we are not interested in loop. Okay, so in a graph theory we are going to consider the actually minimal case, therefore we are not interested in this loop actually. Okay, so either direction, whether it is not this will not actually help. So we are going to consider the loopless graph actually contains but multi-edges graph. So here you can see these are multi-edges, more than one edge between a pair of vertices, though the different directions are different, they are multi-edges, or parallel edges or multiple edges, something like that. So the graph Z contains no loops but multi-edges between V and V is not equal to E in either direction. Okay, either direction it is possible. So these two terms, okay, gives a formula for the number TZ. TZ is nothing but the spanning trees of an undirected graph. Okay, here we have arborescence converging to U and arborescence diverging to U, number of arborescence. So we can have the corresponding actually concept, that is the number of spanning trees, okay, of an undirected graph Z with the help of this concept. Okay, so how can we do this? Say we are given as an undirected graph, so we replace each edge VU, okay, a pair of directed edges, okay, directed edges in either direction. Okay, we are going to replace each edge here. This is a graph is given, something like that. Okay, so graph is given, so replace a pair of directed edges. So you are just to consider, if this is okay, something like that. Okay, this is something like that. It's every vertex, it's an every vertex. Okay, something like that. Okay, it's an every vertex. Okay, so first objective we are going to do this, and resulting graph is said to be this graph is equal to z dash. Our original graph is, this is the original graph. Okay, this is the original graph, something like that, z, and this is the original graph. So resulting, we just doing this, we say the resulting graph is z dash, and you can observe so number of actually spanning tree of z, number of spanning tree of z is same with this, number of spanning tree of z is same with, okay, spanning arborescence actually converging to u, and number of spanning arborescence and diverging to number of spanning arborescence diverging to diverging from u. Now why? Because each spanning arborescence in z dash, that is in the directed graph, converging to u. Okay, if I consider a spanning arborescence converging to u, okay, particular vertex u is converging to u, then it will give actually spanning tree in z. Okay, spanning tree in z. Similarly, if we consider a spanning arborescence in diverging from u, then it will also give a spanning tree in z. Okay, so therefore they are equal. This is very easy to observe. You just consider spanning arborescence converging to u. It's converging to u. Just consider, you just delete. We are interested converging to u means out degree of each vertex other than this vertex must be equal to 0. You just consider this one. This is this out degree. This is this. Okay, you consider this is, then okay, out degree. This is 1. So this don't count this is, okay. Then say this is out degree, na? Okay, so out degree, so you consider this one, out degree must be equal to 0. So this is out degree. Okay, out degree equal to 1 here, out degree equal to 1 here, out degree is 0. Okay, so this is an actually spanning arborescence converging to u. Okay, the these are the edges. You just observe that degree of this vertex equal to 1, degree of this vertex equal to out degree, out degree this is equal to 1, out degree is equal to 0. So this is nothing but actually spanning tree. Okay, spanning tree. Okay, we have no this is actually spanning tree. So they are actually equal. So they are equal. Okay, it's spanning J arborescence E converging to U or diverging from U gives a spanning tree in Z by deleting the orientation. Just you have to delete the orientation. So conversely, if I consider, let T be a spanning tree of Z. Okay, spanning tree of Z, and how can you construct the corresponding arborescence converging to U or diverging to V? So just if we orient the edges of T in the unique direction, okay, unique way towards U. Okay, so this is one, this is one. Okay, so this is unique way we are going to converse. So this is okay. This is actually this is the corresponding. This is a spanning tree of Z. Okay, spanning tree means this is a tree which does not contain any cycle. So we have deleted these edges here. So you can observe each degree of each vertex. This is you say the degree of each vertex, outer degree of each vertex equal to 1. So therefore this is in arborescence converging to U. Okay, so this can be done only one way. Similarly, if I consider, if I reverse the direction, okay, reverse the direction. Okay, if I reverse the direction, then you can observe, then you can have this arborescence diverging from U. Okay, so this is actually true. So if I consider, let T be a spanning arborescence, T be a spanning tree of capital T spanning tree of Z. If we orient each edges of T in the unique way toward U or away from U, gives a spanning arborescence in Z. And these correspondence are clearly bijection. It is obvious from spanning tree you get this converging arborescence or diverging arborescence. So this correspondence is unique. So therefore we have this result. Okay, we have this result. So now you see we can give this matrix, static matrix T theorem. So before this static matrix T theorem, we need some concept of matrix. So Laplace matrix. What is this Laplace matrix? G be a directed loopless graph with these are the vertices. And we denote this is a matrix. So what is this n by n matrix? And entries are number of directed edges from ei to j. Okay, I to j, directed edges from I to j. Okay, directed edges from I to j. Say this vertex I have considered this one. Say this is the graph. This is this one. So this is a B C D, something like that. So I have this A B C D, B C D. So there is no edge in between A and A. If there exists the edge between A and B, is there exists? No, there is no edge between A and B. There is in A and C. Yes, A to C. Okay, 1 degree. A to D, no. Then B to A, B to A, no. Then B to B, no. B to C, B to C, no. B to C, B to D, yes, something like that. So you can have the corresponding matrix. Okay, we can have this corresponding matrix. This the matrix is okay, directed graph. So with this loopless directed graph and this Aij. So let D dash the diagonal matrix D dash and D negative and D positive with the diagonal out degree, with the diagonal out degree respectively, out degree or in degree. This one actually out degree and this one in degree. So you just consider the diagonal elements whose out degrees consider D negative, means diagonal matrix n by n says out in degree. And the Laplace matrices, we have two Laplace matrices. Okay, one is out degree matrix and one is in degree matrix, something like that. And D negative minus A, and this is actually D positive minus A. So what is this actually? That is matrix theorem. So if I consider this is a loopless directed graph, okay, for any ST, whenever ST is possible. So this is the spanning arborescence converging to U. This is the number of spanning arborescence which silhouette actually Laplace matrix. Okay, Laplace matrix. So here Laplace matrix ST. So something like that for any matrix. This is nothing but actually after deleting the many matrix. This is say n by n matrix after deleting S rows and T column. This is submatrix where we have where row S and column T have been deleted. Okay, so these are the actually relation between this spanning arborescence. Okay, spanning arborescence converging to S. Okay, spanning arborescence diverging from S in terms of Laplace matrix. Okay, out degree Laplace matrix and in degree Laplace matrix after deleting the S row and T columns. Here T row and S column. Okay, so you just verify this theorem with the help of an example. Okay, this type of example you can verify this theorem. Okay, so this is the statement and you just verify this theorem with the help of this type of example. Verification is needed. Okay, thank you.